Hi. So I thought I'd just spend a couple minutes recognizing that there are other things going on outside of the classroom today. And thank you all for coming, whoever, those people that came. I presumed on some level your motivation is to learn stuff. I think that's noble. And I also want to thank the people that aren't here, that are making a different decision to not be here. If you're watching the webcast, hi, and you're making a different decision, and which I hope, on some other level is sort of a noble thing to do, a good thing to do. So following your conscience and speaking out, protesting. I think when things get bad in any kind of situation, you can kind of sit back and do the best you can, or you can do what some people are doing today, which is to sort of stand up and say, that it's not okay. And I have to say personally, on a certain level, I feel a little bit lame for being here today. That I do have opinions, and I do think that the situation is bad, and on some level, I feel like I ought to, take a stand on that level. But sort of for a variety of reasons, I don't know if I should go into everything, but for a variety of reasons, I'm not. I'll just say a little bit about my personal situation, which is that as a lecturer, I'm a lecturer, not a professor. You may or may not know that. I am in a union, and the contract states that we can't have walkouts. So the flip side of that is that our salaries are protected. They're smaller, but they're protected. So last semester there was a faculty walkout. Various groups walked out at different points, but the logic of the faculty walkout to some extent was that there was this furlough policy, which I think was, I found a little bit offensive to give professors a furlough with the stipulation that you're going to have a reduction in salary, and you're going to have a reduction in salary, but you don't have to work on certain days. But you can't choose teaching days for the days you don't work. So for a professor, that sort of means that you're sort of not doing research on these other days. Well, it's not like people who are doing research are going to say, well, I have this paper to publish, but today I'll take the day off and just sort of let it go and not do anything today because this is my furlough day. So yeah, I sort of feel like from a professor standpoint, or from especially for someone who's trying to get tenure, that's a little bit let's use the word offensive. I feel like if a professor who's trying to get tenure chooses not to do research on a day, they're sort of shooting themselves in the foot and sort of saying, well, I'm going to hurt my future by being less productive because of this furlough thing. So where the university sort of designates that as a furlough, I sort of feel like it's just a sort of a pay cut. And I realize times are tough, but I guess I feel like it's unreasonable for administrators to make these sorts of decisions when the administrators themselves are earning considerably more money than the rest of us. And another thing that I want to just point out that I think is a little bit hypocritical is that I think that the usual argument as to why the people earning lots of money, so they over, $200,000 a year is a sort of large amount of money that some people earn. The argument that's made that administrators need to earn this much money is that if they aren't given this much money, they'll go somewhere else. We can't attract the best executives and administrators without paying this amount of money. Well, I guess I have two questions. One is it true, sort of, if we cut the highest salaries and made them all $200,000, for example, how many people would leave? And I guess on some level, I kind of question those people's commitment to the public educational system if they're unwilling to work for $200,000 a year because it's not enough money. So that's one kind of gripe I have. If they wouldn't leave, if they in fact would stay for $200,000 a year, great. But if they do leave, are the people that we would get to replace them so much worse? How much worse off would we be if we had these administrators, so the best we could get for $200,000 a year. So I guess, that's, I just want to, speak my mind a little bit on that little bit. I guess I wanted to also just let people talk for a few minutes if anyone has anything that they want to say or add or speak in favor or against anything that's going on. Does anybody have any thoughts? You're not mic'd, so there's no record of you. Anyone want to say anything? Okay, so that's basically what I want to say on the general matter. It's I think. So I recognize that times are tough economically, and we have to make decisions. I guess there's one more thing I want to maybe say, which is that I think that the administration mostly tries to say that UC is a great place to get an education, and we're doing, in spite of all these budget cuts, still a great place to get an education. Everything's great, on some level. And I think that the many faculty feel like, especially if we've been here for a little while, that, well, things are worse than they have been, and we're trying to do more with less. For example, for this class, there used to be 2 discussion sections a week. Now there's 1. Each GSI is responsible for 100 students instead of used to be 80, which is still sort of a lot. Your ability to access and get, learn from your GSI and from me is somewhat diminished by having big classes and stuff like that. And I feel like it's a little bit the responsibility of the administration to get that message out too, to get out the message that to legislatures and whatever that, when the budget goes down, there are effects of that, and the effect to some extent is a degradation of the quality of the undergraduate education. Of course, there's this other effect that you guys have to pay more, right? And that sucks too. And I think the university isn't really being honest when they say that, access to education, diversity of the student body isn't a problem. It's still as good as it ever was. I don't think it's quite true. So if you read some of the go to a picket line and talk to some people, read the literature, I think that you educate yourself. I think you'll find that's it's not accurate to say that we should expect that the student body will sort of have the same demographic makeup. We'll have just as many minorities and low-income kids in the future as we have now, and that sort of again everything's great. I feel like is somewhat the picture that the administration is trying to paint. Okay, all right, I'll stop. Okay, so any questions? Yeah. I don't have a baby girl yet. Thanks for asking. My baby girl is due on March 27th. So, these things are not quite, due dates are not quite, necessarily accurate. My first baby was born a week early. We'll see when this happens. So you'll know when I have a baby because I won't be here for a little while. I have a substitute lined up. Roger Purvis, who's one of the co-authors of your book, will be doing, I think, a couple of lectures. And if I end up needing to be gone for longer than a couple of lectures, there's a good graduate student that has taught SAT 2 for summer school before, and she might do a lecture or two in emergency. So the due date is towards the end of spring break. So, if it sort of happens during spring break, I might just have Roger Purvis do a couple lectures, and then that's all that I'll miss. But yeah, I'll definitely miss, I think, a lecture or two at least. So, any other questions? Okay, so I don't really, have stuff prepared to do. I can just do problems from the study guide, and there are some that I have in mind that are on the harder side, but if anyone has any suggestions of problems that they'd like to see, if you started to do some that you think are hard or whatever, or homework problems that you remember that were hard, or topics that you want me to talk more about? Anything? Any suggestions? Yeah. Sure. Why don't you suggest a problem? Good choice. That was going to be my first choice. So number 18 from the study guide. This, I think, is the hardest problem. So I'll write it real quick if you don't have it. And so he made the comment that there's a lot of problems like this, especially from pervasive problems where you have to deal with the RMS or SD or something like that. So this is a summation idea. Okay, so the average of a bunch of numbers is 108. So a statistician calculates the RMS of the deviations from average and gets 5. Unfortunately, he happened to misread the average of the list as 106 and use that instead of 108 when calculating the deviations. So the SD is not actually 5. Find the correct SD. Okay, so the mistake is to calculate the RMS of the deviations from average using 106 instead of 108. So if we think about what that means in summation notation, this is what the statistician is doing. Take a deviation from, accidentally using 106 instead of 108. Take the deviations from 106, take the RMS of those, and that is calculated as 5. Okay? And I just want to make the point that this is not the same as this. Okay? And I'll say, well, I'll maybe explain why that's true after I do the problem, but I'll say a couple words about it. So what the problem literally says is that the statistician calculates the RMS from the deviations from average accidentally using 106 instead of 108. The problem doesn't say the statistician calculates the SD. Okay? And there's a difference between those because I realize RMS of deviations from average is the same as the SD, but this is not the same as the SD, right? And this the going back and forth from formula to formula. So we do know in general that the SD is this. Square root of that, okay? So this is the RMS of the deviations from average. Deviations from average, square them, take the mean, take the square root. This is equal to that. So these two things are equal, but if you go back and go through the derivation of showing that these two things are equal, it relies on this being the average. Okay? If you have some other number here, then you don't know if these two things are going to be equal or not. All right? So that's a little bit tricky to show. So I don't think I'll do that unless people really want me to. But I just want you to at least recognize that these two things are equal, partly because this is the average here. When you sort of do the math here, there's some cancellation that happens only because this value is the average. If this value is something else, like 106, then you shouldn't expect that the RMS of the deviations from 106 is the same as this. Because if you do the math, you won't get that same cancellation. And I'll maybe show you a little bit of that calculation as we solve for this. Okay? So if you do the problem trying to say that 5 is this, then it won't work. All right. Any questions about that? Okay, so at least I'll start doing the problem, and then I'll talk just a little bit more about why that's not the same. Why the top line is not equal. Okay, so if we square both sides there, we get sum xi minus 106 squared over n is equal to 5 squared. I'm just taking that first part, the left part there, and squaring both sides. All my sums are going to be from 1 to n. I think I won't write it out, right? I equals 1 to n for all the sums here. And then if I expand this, I get sum of xi squared over n. Okay, that's the first part, minus 2 times 106 xi. Sorry, sum of that over n. And then the last part is going to be plus sum of 106 squared over n. Okay, so all that's equal to 25. Okay, so I'm just expanding out this sum and dividing it up into 3 different parts. So there's the first part, sum of xi squared over n, and then the cross term, 2 times 106 times xi, and then the last part, 106 squared. Okay, so now what I'd like to do is solve for this. And the reason why I'd like to do that is I'd like to eventually find the SD. And I can do it this way, okay? So this is the sort of, this truly is the SD. So if I can solve for this part, I know this is 108. I can plug it in and then solve for the SD. Okay, so my motivation is to solve for this. And then this part becomes, I'm going to pull out all the constants, so minus 2 times 106. And what I'm left with is the sum of xi over n, right? And then add to that this. So this is, if I add up a constant n times, I get n times that constant, and then divide by n. So this is actually just going to be 106 squared. So it's 25. So one way you might think about this is that you basically have 106 squared plus 106 squared plus 106 squared plus 106 squared n times. Divided by n, you just get 106 squared. OK, so now I'll put everything else over there. We get sum xi squared over n. And this here, sum of the xi's over n, what's that? That's the average. And is it 106 or 108? It's 108. So the statistician that's doing this math is not actually doing this calculation. What the statistician's actually doing is taking each value, subtracting off 106, squaring it, adding them all up, dividing by n, right? And then taking the square root to get 5. So the statistician actually isn't doing this, right? They're not, this person is not doing this math and getting to a point here where they have to plug in the average. So they don't have a chance to make this mistake. What they're doing is just plugging in the values here and subtracting off 106 from each of them. So once you put a 106 here, there aren't any mistakes left for the statistician to make, right? Whatever mistake they made putting 106 here is already done. The actual xi values are presumably the right ones, and they have an average of n. So if you literally added up the xi values divided by n, you should just get 108. Okay? The statistician isn't making some additional mistake in that part, right? They're just making the mistake of using the wrong average here. Okay, so if I throw that to the other side, I get, there's a minus here, so put it on the other side, I get 2 times 106 times 108, and then plus 106 squared, and then plus this 25. Okay, so that gives you all that. And I'm not sure what that is offhand. You can do the math there. If anyone has a calculator, you can do it really quick if you want. 2 times 106 times 108 plus 106 squared plus 25. Yes? Thank you. Yeah, this should be minus. Right? Putting that over there. OK, any other comments, corrections? So yeah, like I say, if anyone does that, raise your hand and you can tell me the number. But all I'm going to do is I'm going to plug it into that formula, basically. So the SD. Sorry? Well, you're talking about the answer at the end. 11,065? 685. OK. So that minus 108 squared now. We're actually doing it right this time. So we're using the actual average. This is this. And that comes out to be 4.58. Yeah. OK. So this is this. This is 11,685. Okay, so something I want to point out here is that if this really were the average, okay, if I really stuck 108 here, what would happen in this line is I would get 2 times 108 squared plus 108 squared. Right? If I didn't make this mistake that the statistician does, I'd have a 108 here, I'd have a 108 here, and this would be 108. So I'd have minus 2 times 108 squared plus 108 squared, which would give me minus 1 108 squared, which is what this formula says, right? This formula says it should be this minus average squared. And you can see that this is not, you don't get these two to cancel because here you have 108, but the other places you have 106. If these 106s were instead 108s, then you'd get the cancellation, which would give you minus the average squared there, okay? So that's why you can't just jump to this formula, because actually if you're using something that's not 108 here, you don't get it. You don't get these two things to be the same. Okay? So, yeah.
Can you just repeat the question?
Yes. So the average of a list of numbers is 108. A statistician calculates the RMS of the deviations from average for the list and gets 5. Okay? So that's, say this, average is 108. RMS, the deviations from average is 5. Okay, so unfortunately, he happened to misread the average of the list as 106 and use that instead of 108 when calculating the deviations. Okay? So the SD is not 5. Find the correct SD. Does that make sense? Okay. So the wording here is kind of specific and important. It doesn't just say he calculates the SD. If it just said he calculates the SD, it's unclear which formula that he used. It literally says he calculates the deviations from average, and when he calculates the deviations from average, he subtracts 106 instead of 108. Okay. So that problem is hard, and I think it's a little bit weird. It's got this element that's common to the RMS and summation problems, which is that you want to solve for this kind of a thing, average of the squared values, solve for it, and then use it in the SD formula. Okay, so that's a very common theme for these summation and RMS problems. It's got this additional twist, which is that you have to recognize that you have to use that formula and not that other formula, which is what you usually use when you do these RMS problems or summation problems. Okay, questions? Yeah. How to get the median from a histogram? How do you get the average if it's? Say it once more. I can't quite hear you. You said if you have two median values, how do you select one? Oh. If you have 100 values, how do you find the median? Yeah, so put them in order. And the median is the, in that case, if you want to have half the values on either side, you can have 50 to the left, 50 to the right. So it should be somewhere between the 50th and the 51st value. And the convention is to take the average of those two. So if you have a list of 100 numbers, so kind of put them in order. And then find the average of 50th and the 51st. Okay? Those might be the same, right? I mean, the 50th and 51st numbers might be the same, so then it'd just be whatever that value is. But in general, that's what you should do to find the median. So to find median. If there are an odd number of numbers, so like if you had 99 numbers, you can't sort of have half on one side, half on the other. What you would have is you have one kind of literally in the middle, and then 49 on either side. So we have 99 numbers. It's the 50th value that would be the median. And that, like I say, that value would have 49 numbers on either side. Okay? Yeah?
There's this question, special review exercises, the first one.
Review exercises? What chapter?
Special review.
Oh, special review? Uh-huh. End of the 15th? Uh-huh. Which one?
The one that says the murders in 1990 were 20,276 compared to...
Can you just tell me the number?
Oh, wait. Page number is 260.
Wait, 262? 262 for me is the review exercises, not the special review exercises.
I mean,
263, okay. First problem. Okay, got it. Okay, so I'll just read it to everyone. In the US in 1990, 20,273 people were murdered compared to 16,848 in 1970, nearly a 20% increase. True or false? Explain briefly. These figures show the United States became a more violent society over that period, 1970 to 1990. So this is special review. And this is after chapter 15. So it's on page 263 if you want to find this for yourself. And it's number 1. Okay, so again, it's saying in 1990, we have 20,273 murders. It's actually not, it's not so important what the numbers are. And in 1970, we have 16,848 murders. So again, it says true or false, explain briefly. Is this evidence that the United States has become a more violent society from 1970 to 1990? So, yeah, you'd like to know what the rate is, right? The population goes up from 1970 to 1990, and so this is about a 20% increase, it says, or more than a 20% increase. Sort of like to know if the population went up by 20% during that period of time, and if it did, then that's sort of what you'd expect. Is you'd expect the number of murders, essentially you expect the murder rate to be constant. If you want to make an argument that the United States became a more violent society, then you should look at the rates. So, yeah? Okay. Any other questions? Yeah. Sorry? Well, okay, so even if you knew the rates, there's some question as to whether or not the murder rate is a good indication of whether or not the society becomes more violent, I guess, is what you're saying. So if you accept the murder rate as some indication of the level of violence in society, then I guess you can make an argument at least that if the murder rate goes up, then the society is more violent. But yeah, there's a question as to whether or not, like, what do you mean by having a more violent society? Maybe you just define that as meaning, well, there are more murders, or the murder rate defines what the level of violence in the society is. You might also be curious as to what the level of assault is, or rape, or other violent crimes, and maybe those are also an indication of the level of violence in society. I mean, you might also wonder about things like. You might wonder about imprisonment rate. For example, if the imprisonment rate went down a lot over that, it didn't, but if it went down a lot over that period of time, you might expect that there would be more murders because there are more people out in the streets that are basically criminals. And if the imprisonment rate went up, which it did, you might think that that number should go down. So it might be that an indication the murder rate is constant in spite of putting lots and lots of people in prison might be an indication that there's either something wrong with the criminal justice system, on some level that we're not able to prevent murders by putting more people in prison, or it might be an indication that in fact the society has gotten more violent. It's just that since we're throwing so many people in prison, we're able to sort of keep the murder rate steady, okay, in spite of a possible trend that people are getting more violent. So that's sort of a long explanation. The point of this problem is just that the population is going up, so of course you'd expect the number of murders to go up and to make that comparison. Okay? Any other thoughts on this or questions? Other questions? Yeah. Purposes 9D. Oh yeah, so this is that, this is histogram question. And maybe I'll just sketch the histogram really quick. So study guide, Purvis, number 9D. Okay, so I'll draw this as well as I can. Okay, so we have an axis here, and so the label isn't given on the y-axis, but you have these heights of bars here. This is up here 5. So you can sort of look at things match up. This first mark corresponds to these bars. These bars are 2 high, and then this big bar in the middle is 5 high. So 40 is at the middle of that big bar in the center. So the question is, for D, is the average income, these are incomes, is the average income under 40,000, over 40,000, or equal to 40,000? Pick one and explain why. So the average should be the balancing point. So basically what you want to think about here is, will this histogram balance at 40 or not? And this is like a little bit like, it's pretty specific. If you want to think about whether or not this balances, it's almost symmetrical, okay? Now, what would you have to do to make this symmetrical? Can anyone see and describe it? Sorry?
Maybe
lower the first bar to there. Would that make it symmetrical? And raise that one? Okay, so basically what you would do is let's sort of take this little block and move it over to there, and then it would be symmetrical. If I sort of just move those people to there. Then the average would be 40. So it would balance because it's symmetrical. So by moving it to the left there, what's going to happen? It'll tip over, right? If this would balance, and then I take this part and move it to here, where it actually is, then it's going to tip over if I try to balance it at 40. So the average must be to the left of 40. Okay? So that's, you have to look at it pretty carefully, I think, to recognize that. But once you recognize that, then hopefully you see that it's not going to balance at 40. It's going to balance a little bit to the left. And the average would actually be quite close to 40. It's not like crazy lopsided or anything, or skewed, but it's a little bit asymmetrical. It has a little bit of more stuff here that's farther away, so that would tip over at 40. So average is less than 40. Okay? Does that make sense? Okay. Any other comments, questions? Yeah. For D, I'm sorry, for mine or purposes? 24B. Okay. Oh. 24B. The chance that neither Oliver nor Tanya win. Okay, so this is this dice game. And So there's this game, and each player picks a number from 1 to 6 and bets on it, and then a die is rolled 4 times. If that player's number shows up 1 or more times, the player wins. If it doesn't show up, the player loses. So 6 people are playing this game, and their names, and they all have numbers. Oliver has 1, and Tanya has 2. So part B says, so study guide, Purvis, number 24. B. Says, find the chance that neither Oliver nor Tanya win. So Oliver picks 1s, Tanya picks 2s. So if neither Oliver nor Tanya win, that means that none of the rolls are 1 or 2. Okay? So 4 die rolls, and like I say, Oliver picks 1s, so there can't be any 1s, there can't be any 2s. Okay? So anyone want to do it from there? Or? What's the chance you roll a die 4 times and you don't get any 1s or 2s? Not quite right. Someone said 1 minus the chance that you said never get 3, 4, 5, or 6? You only get 3, 4, 5, or 6. So it's not 1 minus that. It's just that, right? Yeah. Okay. Yeah. So this is the chance. If you don't get any 1s or 2s, all of the rolls must be 3, 4, 5, or 6. So one way to think about it is the first roll has to be 3, 4, 5, or 6. That's 4/6, and raise that to the 4th power. It's like first roll is not a 1 or a 2, so it's a 3, 4, 5, or 6. And second roll is a 3, 4, 5, or 6, and the third roll and the 4th roll. Just multiply those all out. They're all independent. Okay? More questions on that? Yeah. Yeah, sure. So part C says Oliver, I want to find the probability that Oliver and Tanya win. But no one else. Okay, so if Oliver and Tanya both win, you know somehow there has to be at least one of the rolls has to be a 1, at least one of the rolls has to be a 2, and there aren't any other rolls. All the rolls are 1s or 2s. So there are a couple different ways to do that. I think the easiest way to me is to say this is equal to the probability that all the rolls are 1s and 2s. So that guarantees that no one else wins. But that's not quite all. If you knew that all the rolls were 1s and 2s, that wouldn't guarantee that both Oliver and Tanya win, because it could be that all the rolls are 1s, or it could be that all the rolls are 2s. So if you just did this, if you just did 2/6 to the 4th, you'd be including this possibility that they might all be 1s, and you'd also be including the possibility that they're all 2s. But not all 1s and not all 2s. Okay? So to get rid of those possibilities, I guess I'll just write that here. We're going to get this, but we need to subtract out these, okay? Because not all 1s is part of that. Not all 2s is also part of that. So this is going to be 2/6 to the 4th minus 1/6 to the 4th minus 1/6 to the 4th. Or if you like, you could just write it as 2/6 to the 4th minus 2 times 1/6 to the 4th. So again, this deals with the possibility that all the rolls might be 1s, and you don't want that. If all the rolls are 1s, then Oliver wins, but Tanya doesn't. If all the rolls are 2s, then Tanya wins, but Oliver doesn't. So you want to include all the ways that you get all the rolls to be 1s or 2s, except for those. Okay? So I'll do it a different way also, but I think this is a little bit easier, or at least cleverer. Another way to think about it is that you might to sort of list the possibilities. You might have So possibilities. You could get, I'll just draw them. Get 1 die marked 1, 3 dice marked 2. Or you might get 2 of each. Or you might get 3 1s and 1 2. Okay? So then you can go through the probabilities of each of those. So this could happen in any order. So you should have 4 factorial, 1 factorial, 3 factorial. So that's the number of ways of mixing up like 1, 2, 2, 2, or 2, 1, 2, 2, or whatever, all the ways to do it. And this is the probability of getting that to happen. So this is like the binomial, but it's not quite, because these two things aren't complements. If ordinarily when you do binomial, you'd have something like 1/6 to the 1 times 5/6 to the third for all the like these would represent all the rolls that you didn't get there. For this, you don't quite have that because the logic is still the same. You're just thinking about this is the probability of one particular sequence of like 1, 2, 2, 2. Okay, but that could happen. So the probability of this particular sequence is 1/6 chance of getting a 1, 1/6 chance of getting a 2, 3 times. And then this is the number of ways of mixing this up. Okay, so you still have this way, you have to count the number of ways it could happen, and then you have this thing you have this part that tells you the probability of one particular sequence. So this one, the next one is going to be 4 factorial over 2 factorial, 2 factorial, and it's really the same, right? But it's still it's 1/6 to the 4th overall, but it's like 1, 1, 2, 2, and then all the ways to mix those up. The last one is the same as the first one. It's 4 factorial. I'll write it as 3 factorial, 1 factorial, but it's the same. 1/6 cubed times 1/6. Okay? So if you wanted, you could add these up. So that plus that plus that is another way to do it. And maybe I'll just do that. So this is equal to, so this is 4. 4 factorial divided by, the 1 factorial is just 1. 4 factorial divided by 3 factorial is 4 times 1/6 to the 4th. They all have 1/6 to the 4th. I'll just write that out in front. And then the first term has 4 ways. The second term has 6 ways. This is 4 times 3 times 2 is 24 divided by 4 is 6 ways. And then the last one has 4 ways. Okay, so this is a total of 14 times 1/6 to the 4th. And just to check, this is 2 to the 4th power is 16 divided by 6 to the 4th minus 2 divided by 6 to the 4th. So 16 minus 2 is 14 times 1/6 to the 4th. So it checks. So give you the same answer. So like I say, either way, I think this is a little bit easier because you don't have to rely on the binomial. But that's also a perfectly reasonable way to do it, and it's not too bad. It's not too much longer. Okay? Questions on that? Yeah. I'm sorry?
Even if, intuitively we know how to do the problem like that without the binomial formula, are you expecting that, on the midterm, that we show our work using a question like that?
He said, even if intuitively you know how to do it without using the binomial formula, do we need to show our work using the binomial? You mean the first method or the second method? The first method, that's fine. If you just did it the way I did it, that's fine. I think that's the way I'd expect you to do it, but sometimes people think that the second way is a little bit more straightforward because you don't have to think about the fact that not all 1s and not all 2s are excluded from that. So I don't know. Yeah, either way is fine. Having said that, there's certainly problems I could ask that you'd need to use the binomial formula. But yeah, for this one, it's fine to not use it. Okay? Yeah? That thing with the histogram? Let's see, where'd that go? So the average is the balancing point of a histogram. And the point I was making is that if you move this over, this is symmetrical, right? And since it's symmetrical, it should balance at 40. So in reality, that isn't there, it's to the left. So if I take that block, I mean, if you sort of imagine this as a solid object and take that block and move it to the left, and it used to balance here, it's not going to balance anymore. You move that over and it'll tip over. So now you know that the average has to be a little bit less than 40. Yeah? Okay. Any other questions? New questions? Okay, well, it's about time I would normally take a break. So since there are no immediate questions, I'll take a little break. If people are truly out of questions, then maybe you'll leave. Otherwise, you may think of a question or two that you want to ask me. Okay? Okay, so a little break. Okay, so I got some requests, things to do, and I guess the first one I'm going to do is the quiz problem. So someone asked to see from the last quiz, 1 parts B and C. Oops. Okay. So this is quiz 3, 1, B, and C. So we have a midterm and a final. The midterm average is 70 with an SD of 10. And the final average is, oh, sorry, we don't know. We don't know the average and the SD on the final. We just, I'm sorry, actually, I guess for B and C we do. For B and C, we know the final has an average of 50 with an SD of 10. And we know the correlation is 0.6. And we know that the scatter diagram is football shaped and the scores on both exams are continuous. Just in terms of doing, yeah. Okay, so of the students that scored 50 on the midterm, about what percentage received a higher score on the final than on the midterm? Okay, so here's our scatter diagram. And here's 70, here's 50. So we're talking about people that got 50 on the midterm. And we're curious about what percentage of them got a higher score on the final than the midterm. So that means they must have gotten above 50 on the final. So one way you might think about this is that there's this vertical strip here. The scores in that strip follow the normal curve. And I'd like to know what percentage of them are above that point, above 50. Okay, so just look at that sideways. And so if I redraw that, I have some average in this strip. I can find that using regression. That's going to be my new average. And presumably that's, so if you're below average on the midterm, you should expect to be below average on the final. So the new average should be somewhat below 50. So 50 is, I can draw 50 up here somewhere. And I want to find that area. So to do that, I want to convert to standard units. I'm going to take 50, this value, subtract off the new average, divide by the new SD, which is the RMS error. RMS error gives you this spread within each vertical strip. Okay, so that's the kind of big picture thing. So in terms of how to do problems like this, the way you recognize that there's a vertical strip problem is that everyone has the same midterm score. They all have 50 points on the midterm. So that's what tells you you're working in a vertical strip. Once you realize you're working in a vertical strip, then all these problems look more or less the same. You find some value, subtract the new average, and divide by the new SD. So new average is what we get by doing regression. So we convert 50 to standard units. 50 minus 70 divided by SD of 10 is minus 2. Multiply by R. So this is SU. And then multiply by R. So times R would be minus 2 times 0.6 is minus 1.2. And then convert out of standard units out of SU. So this gives us minus 2 SDs from the average, below the average on the final. So the final has a SD of 10 and an average of 50. So this is 12 points below average, or 38. Okay? So that's the new average in the center there. And then the new SD is RMS error. It's the tells us the spread in vertical strips, and because it's football shaped, the RMS error is the same in every vertical strip. So we can just use RMS error everywhere, which is 1 minus R squared times SD of y is 10, SD on the final, and that comes out to be 8. So now we're ready to convert that into standard units. So we have 50 minus the new average of 38 divided by the new SD of 8. So 12 over 8 which is 1.5. And look up 1.5. So 1.5 gives us 86.64 in the middle. So it's, I guess, a little bit less than 7%. 6 point, so 100 minus 86.64 over 2 is, what, about 6.7 something? About that. I guess a little bit less than that. Okay? So that's that. Questions? Okay, so yeah. I was asked to do C also, so this is part B. So I'll do part C, and then actually I had another question, a couple of other questions that people asked me during the little break, so I'll do those first. You're going to ask me about purpose number 7, though? Yeah. Okay. Okay, so let me do the C part. The C part, yeah. Sure. Yeah, I'll do C and then I'll do A. So to receive an A in the class, student needs the sum of the two scores to be at least 160. Your friend got an A, claims to have received an A, and the friend scored an 80 on the midterm. So essentially, you're just trying to figure out what's the chance of the people that scored an 80 on the midterm, what percentage of them managed to get above 80 on the final. So it's a similar problem. So we have 70 up here, 80 up here. So convert to standard units. We get 80 minus 70 over 10 is 1. So your friend got 1 SD above average on the midterm and predicted to get 0.6 SDs above average on the final. 0.6 SDs above average on the final would be 56. Okay, and so to get above 80, we already found the RMS error, so 80 minus the new average of 56 divided by 8. This is, 24 over 8 equals 3. So there's our value in standard units. So I think it's 99.73 in the middle. So this is about, I guess, 100 minus 99.73 over 2 is 0.135. Okay. It's a little bit more than 0.1%. So not so likely. So I think that the implication here is that you're suspicious of your friend. Okay, and then for A, did you want me to do the original version or the amended version? I thought it was kind of hard, and actually, I'll be honest. When I first looked at it, I didn't think you could do it, and you can't do it. Sure. Okay, so A. What I have here is the original version, so I guess I'll do that first. Of the students who scored 50 points on the midterm. So yeah, so GSA wrote this, and I was like, huh, I thought the GSI made a mistake. And then I didn't look at it carefully, because I had made a suggestion to the GSI about a kind of problem to do, and he came back with this problem, and it wasn't what I was expecting. So yeah, then once I thought about it, I realized, oh, you actually can do this. So then of the students that got 50 on the midterm, how many scored below the 4th percentile in the final? So if you got 50 on the midterm, we know that you are minus 2 in standard units. You're predicted to be minus 1.2 SDs below average. So prediction, final score, is 1.2 SDs below average. Okay, so if you want to think about that, you don't know the average in the SD, but you can write that as minus 1.2 times the SD of y, SD on the final, plus the average on the final. Okay? So I'll just think about this as my predicted value. That's my new average. Okay? And we don't know what the RMS error is exactly because we don't know the SD of y. But we do know that the RMS error is square root of 1 minus 0.6 squared times SDY, which is 0.8 SDY. So I'll just leave it like that. And then what about the fourth percentile? The fourth percentile is minus 1.75 in standard units. Okay, so if you use the normal table, figure out the fourth percentile, you'll get that it's 1.75 SDs below average, which is minus 1.75 times the SDY plus the average. Okay, so you don't know the SDY, you don't know the average, but you can still kind of write these things down, and then what you're interested in doing is this is the value, this is the new average, and this is the new SD. So let's just kind of just go through and take this value, minus 1.75 SDY plus the average, subtract off the new average, which is this, minus 1.2 SDY plus the average, and divide all that by 0.8 SDs. Okay, so you take this and you get average minus the average, so that cancels. We don't care what the average was, right? And then you get minus 1.75 SDY minus negative 1.2 SDs, so that's plus, or sorry, it's still minus, but you add this. So it's minus 0.55 SDY divided by 0.8 SDY. And the SDYs cancel, so it doesn't matter what the SD was. And that, I don't remember offhand what that is. Can anyone do it on a calculator real quick? Let's see, what is it? I guess it's almost 7. What, sorry? I mean, almost 0.7, right? 0.6, okay. Minus 0.69, I'll say. Okay, so round it to minus 0.7. And yeah, so when you do that, minus 0.7 on here. And I'm going to try to find percentage of people above that. Below that, okay. Okay, so I want to do that. And if I look up 0.7 on the table, I get 51.61% in the middle, about 52%. So this is about, if that's 52, then 24. Okay. So that's the original version, and yeah, I guess I think that's a little bit hard. So anyway, so there's that, and then the changed version I think was just to predict the percentile rank of someone of this person, basically, right? So the prediction should be that this person is minus 1.2 SDs from the average, so below average, and if we figure out that as a percentile rank, we get 77% in the middle. So new question A. We've sort of already done the math for it. The prediction should be 1.2 SDs below average. So if we do that, we get 77% in the middle. And this comes out to be, I guess, 11.5%. Okay. So what does it actually ask? Oh, I don't have it, right? Yeah, so I think that's right? That's the question, right? To find, predict the percentile rank for this. Is that right? Okay. Okay, so that's that problem. Let me see what I get through here. Been asked to do problem 22, which is quick. So I'll do that one real quick. So purpose number 22. I think the easiest way to do this is to draw a big grid. And anytime you have like 2 die rolls or 2 draws from a box with numbers, something like that, I think drawing a grid is a good idea because you get it right. If you just kind of try to think it through, I think you might, you have some chance of making a mistake. But I think if you draw out a grid, you're going to get it right. So the grid that you draw here is 1 through 10. Okay, so 1 through 10 here, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so then say this is the first draw, and this is the second. And you want to find the chance that the second number is bigger than twice the first one. So you draw two times at random with replacement from this box. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Find the chance the second number is bigger than twice the first one. So if the first one is a 1, then the second one has to be 3 or more. 2 has to be 5 or more. And then 3, 7 or more. And 4, 9 or 10. And then if the first one's 5 or more, there's no way for it to happen. So you just count. So 8, 14, and 4 is 18, 20. Okay? Now, if you wanted to, if you didn't think of using the picture or whatever, you sort of go through cases. You could think of the chance that the first one's a 1, which is 1/10, times the chance the second one's at least twice, or more than twice. So this would be 1/10 times 8/10 plus 1/10 times 6/10, and just go through each of those, and that'll work too. Okay? Questions on that? Yeah? Just what I said. Just think through, well, how could it happen? So first one could be a 1, and then the other one's 3 or more. It's 1/10 times 8/10. Or you could have first one's a 2, and then the other one's 5 or more. So 1/10 times 6/10, and add those all. Okay? Questions on that? Okay, so I was asked to talk a little bit about the binomial, and so maybe I'll do that last. There's another actual problem, because I could talk about it for a while. So problem 7. Was it all of 7? Yeah? I don't know what the problem is. Oh, yeah, good. Sort of hoping someone would ask me another RMS problem that's a little bit more typical. So this is study guide, Purvis, number 7. So list of numbers has an RMS of 4, and then a new list is made by adding 3 to every number on the list, and the new list has an RMS of 5. So what do you mean by RMS? It means what happens if we take the numbers, square them, take the mean, take the square root. So if the numbers are like xi's, square them, I equals 1 to n, square root. Okay, so square them, take the mean, take the square root. This is the RMS of a list of numbers, and that's 4. Okay, a new list is made by adding 3 to all the numbers, and that list has an RMS of 5. So if we add 3 to all the numbers, we get this. That's adding 3 to all the numbers, square them, take the mean, take the square root. That's equal to 5. And let's just expand this. Okay, so what do we want to find? We want to find the average of the original list and the SD of the original list. Okay, so we certainly need to get the average to get the SD. If we expand this, this is square root of sum I equals 1 to n xi squared plus 6xi plus 9. Just multiplying that out, squaring it, divided by n. Now, let me just say why I know to do this. The reason why I know to do this is that I know the sum of the squares divided by n, And the sum of the squares is also in here. So I can take the sum of the squares, or average of the squares from this, plug it in here, and what I'm going to be left with is the sum of the xi's over n, which is the average. So I can solve for that. But general idea of these problems is it's very frequent that you write down something like this, expand it, and then sort of think about where you can plug something in somewhere else to make your life easier. Okay, so we get this, and I guess I'll square both sides. Maybe I'll just square both sides here too. So sum xi squared over n is equal to 16, and then if I square both sides here, I get 25 equal to sum of xi squared over n plus 6 times the sum of xi over n plus the sum of 9 over n. All the sums are from 1 to n. I'm not writing that in. Okay? And this we know, right? Sum of the xi squared over n we know is 16. And this is 9. Okay, so you have 16 there, you have 9 there. That's equal to 25. So from all this, we get, I guess I'll do one more line. I'll just write, this is equal to 16 plus 6 times sum of xi over n, which is the average, plus 9. Right? If you add up a constant, divide by n, you get the constant. So again, we have 25 over here, 25 over there, so we just get that the average is 0. 6 sum xi over n equals 0, so average is 0. Okay, so that's part A. Oops. Okay, so if we know the average is 0, then in fact, we don't have to do any more work to get the SD, because the SD of the original list is just, so for part B, it's that, but that's 0, right? X bar is 0, so this is equal to minus 0 squared, which is just the RMS of the numbers themselves. So the RMS is 4. Okay. If it were different, you have to play with it a little bit more, right? If it were, if the average turned out to be 1 or something, then we know this is 16. We solve for that, it's 16. So you have to, whatever the average is, subtract it, take the square root, and you get the SD. Okay. So if that hadn't turned out so nice, we'd have to do just a little bit more work there. Okay. Questions? Okay, so sorry I didn't get to talk about the binomial. I will just say I kind of used it in this part that's here. I used the idea of it, that the binomial coefficient gives you the number of ways something happens, and then the other part, the p to the k times 1 minus p to the n minus k, which is not what I have here, but that gives you the probability of a particular sequence of like a bunch of successes, a bunch of failures. All right? So if you can come to my office hours or just look at the lecture on that, you can do that. Okay, so next Tuesday, just a quick comment. If you can get here a little bit earlier, I might move people around. Okay, so get here a little bit early so we can move people around and get started at 2:10. Okay, and all you need is a calculator and something to write with. You could write on the exam. Okay, so I have office hours right now if you want to talk to me or email me before then or whatever. Okay, bye.